Hi everyone, for tuning in to this demo on generative adversarial networks. This is based on an excellent tutorial which you can find here, which has most of the code that we'll describe today. We talked about GANs in the lecture. GANs are a nice way of generating realistic content. The motivation today is that in addition to generating realistic content, we also want to have more control over it. So in our case, we're going to be working with the MNIST dataset, which consists of handwritten digits. And instead of just generating random digits, we want to be able to generate digits that look a particular way. So by the end of today, our goal will be to have a network which we can say, hey, generate a 9 or a 2 or a 3, and it'll do exactly that. Let's describe the general architecture in this image. There's a lot going on, so let's break it down. For now, we'll forget about this real label aspect of it, and we'll just talk about the normal GAN architecture. The GAN architecture consists of a generator and a discriminator. The generator takes in some latent random vector, which is Z, typically generated from a normal distribution of some small size. It takes that in as input, and it creates some output. This output we'll call G of Z is fake data, and it'll be the same size as our real data. Now, the discriminator will take in whatever this dimension is of our data, and we'll pass in real data, and we want it to output that is indeed real data, and we'll pass in fake data, and we want to output that is indeed fake data. We train both of these in conjunction with each other, so it's an adversarial process. The goal is for the discriminator to get better at being able to tell apart random noise from actual images. And as the discriminator gets better, the generator can improve by being able to fool the discriminator and making data that's more realistic. As we iteratively train this process, the hope is that the space of images that are generated by the generator get closer and closer to the real data that we have. And in that way, we're able to successfully train a generator which can fool a discriminator, but also fool us in the sense that it generates images which look realistic to us. Now, the difference between a GAN and a conditional GAN is that a conditional GAN takes additional input, both into the generator and the discriminator. Instead of just getting information of the data, in this case, it'll be an image of a digit, we're also giving it a label, a class label, which corresponds to what that digit should be of. So in the real data, it's very easy. We have an image of a 0 or a 1, and we pass in a real label corresponding to that particular class of a 0 or 1. We concatenate these two together and we pass it to the discriminator. We also do this for the generator, where instead of just passing in this random latent vector Z, we concatenate it with a real label and we pass it into the generator. This gives us some fake image output, and then we combine that with that same real label and we pass it into the discriminator. The intuitive way to think about this is that the task of the discriminator isn't just to determine whether an image is real, it's now also to determine whether an image is real and it belongs to the class that we're being told it belongs to. So before, a discriminator would accept a 0, 1, or a 2, but now if a discriminator gets a 0 and the label 2, it'll say that's actually fake because that's not an image of a 2, that's an image of a 0. By making this task slightly different, we're training the discriminator to use that information of what a 0, 1, or 2 or the true class looks like and telling apart real from fake images. And as the discriminator learns what that image or that label looks like, so the generator also has to learn that in order to fake it. With this high-level understanding in mind, let's jump into the code. As always, we're going to load several libraries. In our case today, we're going to load the MNIST dataset. We're using MNIST again because it's the images in it are very small, they're 28 by 28, which are conducive to quickly training a generator and discriminator from scratch. I want to point this out again because I think it's a great resource. We are using a PyTorch datasets library to load the MNIST dataset here, but there are lots of other datasets if you're interested in working with them. If you Google just PyTorch Vision datasets, it could be MNIST or just datasets in general, you can get to this page. And on this page, there are lots of different datasets with different types of images in it. This is specifically for vision. So for example, we have a celebrity A data set, which contains images of different celebrities, and the attributes or features are different things that appear in these images, such as bangs, pointy nose, or a nasal face. You can also work with lots and lots of other data sets, such as the USPS data set, which I'm not sure what this does. I don't think it has anything to do with USPS, maybe. Not sure. But okay. There are lots of data sets that you can work with if you're interested. Again, we're using MNIST because it's nice and small and we're able to train on it fairly quickly. We'll define several helper functions today. The first helper function will convert the real label of the image, so whether it's the digit 0, 1, 2, 3, etc., into a one-hot encoded vector, and then we'll pass this one-hot encoded vector as input to the generator and the discriminator. In this case, when we pass in the one-hot encoding, or when we try to get the one-hot encoding of 3, this will give us a vector of dimension 10, because that's the number of classes that we have, where there's a 1 in the index 3 position and zeros everywhere else. We're also going to define this handy helper function, which will take in the generator and some random noise, and it'll give us different images. It'll give us 10 images of each one of the 10 different classes, and we'll use this as a way to visualize the training process. Now we'll instantiate the architecture. So we have our data set, some helper functions, we'll instantiate the architecture. The architecture of the generator starts small and it gets bigger. The input size of this is the input size of the latent random vector that we have, plus the number of classes. We're adding this to make it a conditional GAN as opposed to just a regular GAN, and this will hold information about what kind of images we want to generate. We'll pass this through several linear layers that increasingly get larger until we output the image size. In our case, the image size is 28 by 28, which is 784. We're also applying a Liku ReLU, which is a version of a ReLU, except just taking the max of 0, so it's flat, it's slightly slanted. And we're also passing it through different batch normalization layers to make the values more uniform and hopefully more realistic for the images that we want to produce. And then when we take as input, remember there are two inputs that we're getting. One is the actual images, and then the other are the classes. In this step, we concatenate them together so that the input that we get to the network is the image, or sorry, it's not the images, it's the latent vector Z. We get Z and these classes. We pass it through our network. We reshape this into the shape of an image, and then we return it. The generator takes something of the same dimension, 28 by 28, and it'll output a 0, 1, or something close to 0, 1, based on the probability that it thinks this is a real or a fake image. Its input consists of the size of this, and then also the number of classes, so that we can give it information about what images of different classes look like. Just as the generator went from a small input to a large output, we're now going from a large input to a small output, because the input consists of the class that we think the image should be and an image, and it'll output something that's 0, 1, or it'll output a single value, and we'll interpret this as a probability that this image is 0, 1, and we'll train it as such. We need to do the same process so that when we get in this image and a class, we reshape everything and concatenate it together into an input, which we can then pass to the network to get out the binary label. Now that we've defined our architecture, let's set up for training the training process. We're going to use the CUDA device if it's available, because this is a computationally intensive task to train the discriminator and the generator from scratch. We're now going to initialize the discriminator and the generator. I'll call them D and G, and we'll put them on the device. Notice that these are randomly initialized. So nothing here has been pre-trained. We're not calling any default parameters here. These are randomly initialized models. So at first, we think that they'll be absolutely useless, which they are. The generator will output random noise, and the discriminator will output a random signal. But by training them in conjunction with each other, the hope is that they'll both improve over time. We'll train it for 10 epochs, which is very short. We'll specify the size of our noise vector to be 100, and then the step size here, the step will just be how often we want to save different images output by the generator. The training process is a little bit different from what we're used to. We're going to use the criterion of binary cross-entropy loss for both, but remember the discriminator, we want it to be as close to the real labels as possible. So the thing that we pass in, so we want this loss to be low. The generator wants the loss of the discriminator to be as large as possible. So we'll also use binary cross-entropy loss, but we'll make it negative. So minimizing the negative loss will actually maximize it. Because there are two different loss functions here, we'll have two different training steps. There'll be a training step for the discriminator and a training step for the generator. And it's important that when we're training the discriminator, we only update the weights of the discriminator. When we're training the generator, we only update the weights of the generator. This is different from what we normally do because often when we're training, we update all of the weights in the network together. Here, we're doing each one of these in different passes because the objectives that we're training them for are different. We will use these vectors to denote the real images as ones and the fake images as zeros when we're passing them into our generator and our discriminator for the purposes of computing this loss function. Let's take a quick look at the data that we have. We're going to load our images and these class labels. The class labels are the labels of these different images. So it looks like in this image, there's a 1, in this image, there's a 4, in this image, there's a 2. And then we will encode them by doing a one-hot encoding and then put it on the device. This one-hot encoding just gives us an output that looks like this. The reason why is because then we'll pass in this vector as input to our generator and our discriminator. And this will encode the information about what type of image this should be generating or discriminating against. Now we'll do the training process. I will create a directory to save these generated images. I called it samples, and samples consists of these different JPEGs of the outputs of the training process at different steps. You can download them if you want, but we'll visualize them in a second. For each epoch and for each batch of images and class labels, we'll have two training steps. One will be for training the discriminator and one will be for training the generator. In the training discriminator part, we load our images, these are real images, onto the device and we call it X. Then we get our class labels, which will reshape, and then we'll encode them, and then we'll put them on the device. So it'll look like something like this at this point in time. And then we'll pass these real images and the class labels into our model and we'll get some output. And we want this output to be as close to the all ones vector as possible because the all ones vector indicates that these are all real images. So our criteria, our loss will be the difference or the cross entropy loss between the thing we're outputting from the discriminator and this all ones vector. Notice this is only half of the loss. This is just training for the model to output 1 when we're given a real image. We also need to train the model to output 0 when we're given a fake image. We generate fake images by getting the latent random vector z, putting it on the device, passing it and the class labels into the generator so we get some output from it, and then outputting these fake images and the class labels into the discriminator. Now, when we compute the loss, it's the cross entropy loss between the thing that we're outputting and the all zeros vector. This is the discriminator loss for fake images because we want the output on the fake images to be as close to 0 as possible. The total loss consists of the loss on the real images and on the fake images. Once we've computed this loss, we zero out the gradient, we backpropagate, and we only update the parameters of the discriminator. So we're only updating the parameters of the discriminator to get a better discriminator loss. If we were updating the parameters of the generator as well, it would be counterproductive because this would be making the things generated by the generator worse for us, not better. Okay, at this point, we've trained the discriminator. Initially, the job of the discriminator is quite easy because it gets highly structured MNIST images and it only has to tell them apart from random noise. So we expect it to quickly learn to be able to tell the difference between random noise and highly structured images. As the discriminator gets better, we can use that to help train the generator to be able to fool the discriminator. The way we train the generator is that we'll create inputs for it. We'll get our random vector z, we'll pass that and the class labels into our generator. We defined these class labels before, so they're representative of the distribution of class labels in the data set. This will be our fake images, and then we'll pass our fake images and these class labels into the discriminator. The loss is now the cross entropy loss between the outputs we get on these fake images and the all zeros vector. If we just minimize this thing alone, then we would be making the generator try to minimize this loss, which would mean outputting less realistic images. But by multiplying this by -1, when we minimize this, we're actually maximizing this criterion, which means we want the outputs of the discriminator to be as close to the outputs to the output of 1 as possible. So not 0, but 1, indicating that we fooled it. The way this works is that we train by zeroing out the gradient, backpropagating this loss, and then updating only the parameters of the generator. If we are updating both the parameters of the generator and the discriminator, this would be trivial because it would just mean making the discriminator worse. But the only thing that we can control in this process when we update this loss is G, the generator. So the weights of the generator are being trained to better fool the discriminator. So we're going to output images which better fall into the set of images that the discriminator thinks are real. As we train the generator, we'll find some set of images which will fool the discriminator. Chances are that that set of images actually aren't the set of images that we think look like it, because we're in a high dimensional space and there are lots of different subsets of images, and some of them will be able to fool the discriminator, but to us they won't look real. So we have to alternate between training the discriminator and the generator. So the discriminator, whatever the outputs are that we're getting from the generator, will be trained to be able to tell that those are fake. And then the generator will be trained to be able to output more realistic images over time. And as we train for longer and longer, the hope is that the outputs from the generator get more and more realistic. You'll notice that the losses vary over time. If we were doing a normal deep learning setup, this would be concerning because it means we're not learning. But in this case, because we have two different networks competing against each other, this is exactly what we expect. We expect at some points for the generator to improve and at other points for the discriminator to improve. And by both of them, and necessarily if the generator improves, that means that the discriminator will do worse and vice versa. So we expect both of these to increase and decrease over time. And through this tension of this adversarial process, we hope that both of them become better. And then when we use the generator to generate images, using this get sample image helper function that we defined before, we hope that these images will be more and more realistic. Let's plot these images. Initially, if we've done no training whatsoever, we're getting random images from this process that actually just look like random noise. And that's to be expected. But then it gets better over time. After 5,000 steps of this process, 5,000 batches that we've trained on, we get images that look like this. We can also look at earlier on ones. And they're starting to look like images, but maybe we think the 7s look like 9s and the 3 looks like 8s, etc. As we increase the stage that we're looking at for these images, they get better and better. The way that I generated these is, for this first row, I've asked the generator for images that look like zeros, and it's given me these as output. For the second row, I've asked for images that look like ones, and it's given me these, etc. And for each one of these, I generate a special latent vector, which is why each one of these images look different from the rest. As we keep training, the process gets better and better. So the 4s look more like 4s and less like 9s, and the 7s look more like 7s and less like 9s. The 9s look like 9s. And we've gotten to the point where I'm not sure I would say that these are well-written digits, but I can definitely recognize almost all of these as the number that they're supposed to be from, which is quite impressive given that we only trained for 3 minutes, albeit on a powerful T4 GPU. By the time we're done training, even the worst images look like messy handwriting, which is quite lovely that we're able to train this so quickly. The reason we're able to train this so quickly is because the size of each one of these images is very small. It's 28 by 28. If you tried to do this with larger images like the celebrity data set, it would take much longer and be far more computationally intensive. And instead of using linear layers, which are possible for our case because the size of the input and outputs to the linear layer are small, you get something that's way too large if you didn't do that. One thing that I want to note is that GANs have become less popular over time. The reason why is twofold. One is that they're quite computationally intensive to train, and the second is that they suffer from something called mode collapse. If you think about this process, the generator can short circuit or win this process if it learns to output an actual realistic image all of the time on its input. So every time we ask it for a 0, if it actually outputs a perfect 0, then it's won the process because the discriminator won't be able to tell the difference between that image and the true image because that is one of the true images. And the generator won't improve anymore because the discriminator's loss is quite large. And yeah, so this happens in practice. It's called mode collapse. And the issue is that the generator only generates one or a few images rather than the multitude of images that we'd like to see. This especially happens after we've trained for long periods of time. And there are some things that you can try to do to get around it, but none of them work very well. So instead of generating images using GANs, we've now turned to using diffusion and processes like stable diffusion to generate images. And that's what we'll cover next week in the demo. Thanks for tuning in. I hope this was helpful. As always, you can post any questions that you have on the online discussion forum, and you can find this notebook linked to in the description below.